Hello. Well, I was in the middle of this, then everything crashed, and it was terrible. So I have to start over. So you don't get to see the first video. It was awesome. I had these great jokes. Everyone who was listening was rolling on the floor laughing. Oh, it's hysterical. Oh well, all business. All right, you will need your chapter 10 notes. And as you see, the volume formula here is 1/3 area of the base times the height for a pyramid or a cone. And the next question, how many non-overlapping pyramids can you fit into a prism? The answer is 3. And that's assuming that the prism and the pyramid or cone have the same base and the same height. All right, we get to do a proof today. And it's a very fun proof, and it has lots of good geometry stuff in it. And it's so exciting. We haven't done a proof in a long time. I just am overflowing with excitement. Happy, happy, joy, joy. And I'm sure you are too. But you will need to really concentrate. So whatever smartphone apps you're using right now, or whatever else entertaining in your life, you're gonna have to shut that down so you can focus. Otherwise, you're not gonna understand this. So we're gonna derive the volume formula for a sphere, and it's gonna be fantastic. So here's our pretty picture. Mine's in color. Hopefully when you printed this out, yours is in color too, but maybe not, doesn't matter, but color is easier to see. So what we have here is we have a cylinder in yellow with a radius of r, and the height is also the same as the radius, so capital R. And then we have a hemisphere inside, and the base of the hemisphere, a hemisphere is half a sphere, is the same as the base of the cylinder. And then the top of the hemisphere is touching tangent to the top of the cylinder. Then we have an inverted cone. It means it's upside down, and the radius of the cone is the same as the radius of the cylinder. They share the base there. And then the height of the cone is r, just like the height of the cylinder, and the height of the hemisphere is the height of the cone. Okay, so it says, we assume you know the volume of the cylinder. So what is the volume of this whole thing? Well, it's the area of the base times the height. So area of the base is pi r squared, and the height is also r. So we could simplify that as pi r cubed. So far, so small. Now it says so we have this inverted right circular cone in the cylinder with the flat base of the cone at the top of the cylinder and the point at the bottom. We assume you know the volume of a cone. We just put the formula at top, so 1/3 area of the base times the height. In our case, the area of the base is pi r squared, and the height is r. So we get 1/3 pi r cubed. This is fun. Okay, we're going to turn the page. Don't worry, I have the picture on the next page too, because now it's going to get interesting. It says, on any horizontal slice of this configuration, the area of the cross-section of the hemisphere equals the area of the cross-section of the cylinder minus the area of the cross-section of the inverted cone. This is what we're trying to prove. So this is our conjecture. Now, first of all, what is a cross-section? A cross-section is a two-dimensional slice out of a three-dimensional object. And in this case, we'll be taking a horizontal slice. So right here. So it's like if you it's if you've ever, like, let's say you had for Easter dinner, you had ham. And you got this round piece of ham, and you have a meat slicer. And you take that round piece of ham and you put it in your meat slicer, and you cut that, you use your meat slicer, you know, kind of like they have at Myers in the deli or whatever deli you go to. Maybe you have a meat slicer, I don't know. And you take that meat slicer and you cut the smallest shaving that's still a full piece, and you put the ham through the slicer, and you start cutting slices for like lunch meat. And so you get these, so if the base of the ham is circular, you put it through that meat slicer, you'll cut off a circle with a very small height to it, or thickness. And that's a cross section. So in this case, we have our cylinder, and we're cutting a horizontal slice through the center of this. It actually doesn't matter where we cut it. We're just picking an arbitrary spot. And what we're saying is that the distance from the base of my cylinder to where we cut this cross section, we're calling that h, the height above the base where we're cutting this cross section. And then s is the radius of this hemisphere at that spot. So you notice how the hemisphere, like at the very base, we know the radius is r. But as we move up, the radius is changing, right? It's getting smaller and smaller as we go to the top. So we're saying at the spot where it's cut, we're saying the radius is s. So radius of the hemisphere in the cross section. Okay. Similarly, the C represents the radius of the cone. And so it's kind of hard to see here, but this, it's like this spot here. I'm going to trace it and botch it, I know, but so what they're saying is, we're looking at a two-dimensional picture of a three-dimensional deal, but this, that I kind of made it darker. That's your cone at the height of the cross section. And so we're saying C is the radius of the cone cross section. And then obviously the cylinder is still, the cylinder has the same radius all the way up and down. So the radius of the cylinder at the cross sections are. So I drew a top view. So if you're looking down, so you cut the slice out, it's lying there flat on the table. And so if you're looking down, you'll see that this outside is the cylinder cross section. And then you've got the hemisphere cross section circle. And then you have the cone cross section. And so you can see you've got 3 circles here of different radius. Maybe that helps. Okay, so what does the proposition say? The proposition says if we take a slice, here's our slice, any horizontal slice, so it could be anywhere. We put it here just to have an example, but it's arbitrary, meaning it could be anywhere between the base and the top, anywhere between the 2 bases. And what we're arguing is the area of the cross section of the hemisphere, so equals the area of the cross section of the cylinder minus the area of the cross section of the cone. So looking back at here, what we're saying is if we took the area of the hemisphere, which is the green circle here, that is going to equal the area of the cylinder. So this circle, subtract the cone area, which is the inner circle. So what we're saying is that no matter where we cut this slice from, if we take the cylinder cross section and subtract the cone cross section, we're going to get the area of the hemisphere cross section. Now it's important to note that at some spots, like as you get closer to the top, the cone area is going to be bigger than the hemisphere area. And at some spots, like down here, the hemisphere area is going to be bigger than the cone area. But it doesn't make a difference on our proposition. So our proposition is, I'll just write it here, that the hemisphere area is equal to the cylinder area minus the cone area on any horizontal slice. All right. So you can read this here, that this just involves writing out the areas of the three different circles and seeing that the way the radius of the circular cross-section of the hemisphere changes and the way the cross-section of the cone changes match up. So take this arbitrary slice, H above the base. Clearly the cylinder's circular slice is the same throughout. So no matter where we cut the slice, the cylinder is always going to be the full circle with a radius of r. So that's always going to have an area of pi r squared. Right? Now, the area of the circular cross-section of the cone is pi c squared, where c is the radius of the cone at that point. So looking at our picture here, here's our cone cross-section. This circle is going to get bigger or smaller depending on where we take our horizontal slice from. But it's always going to be c. We're labeling it as c. And the area of the circular cross-section of the hemisphere is pi s squared, where s is the radius of the hemisphere at this point. So let's look at this as from a side view. Okay, so this is if we took our cross-section. This is looking at this whole picture here from the side, but instead of looking at it in a three-dimensional drawing, we've reduced it to a two-dimensional drawing. Okay, so here's my hemisphere, here's my cone, and I don't have, I mean, the whole cone's not drawn in. Okay, and then here's a look at what so this is like the cross section. C is the radius of the cone at our cross section, and then the R is the radius of our cone at the top. So, you know, but the other side of the cone's not drawn in. That would be over here, right? That other triangle's not in place. And this is obviously the hemisphere, and the cylinder would go around it, right? So if this was connected down to here, and you drew this piece out and drew up here, I mean, there's your cylinder, right? And then this would be the other side of the cone. Okay, maybe that's easier to understand. All right, clearly the cone is an isosceles triangle. So here is one side, r, and the height of the cone is r. So it forms an isosceles triangle, the height and the radius of the cone. And then this triangle here is similar. So we haven't studied similar triangles yet, but in order for two triangles to be similar, they need to have the same angle measures, and then that way their sides will be in proportion. So if you look here, this top triangle has a 90-degree angle here, and this as well, because this is the height, we know it's perpendicular to the base. So this is also 90 degrees. And then notice that they share this angle. Whatever this angle is, this angle's in both triangles, right? So here's angle 1, angle 2, angle 3 in my big triangle. And then you have angle 1, angle 2, angle 3 in my small triangle. We don't know what this angle is off the top of our head. But we do know that it's equal. Actually, we do know it's not. It's a 45-degree angle. It has to be because it's an isosceles right triangle. So 90 degrees, these are both 45. So because this is in this smaller triangle, this has to be 45 as well, because these three angles have to add to 180. So what that tells us is that H and C have to be the same, because it's isosceles, just like the bigger triangle. So C equals H. So what that means is no matter where we take our horizontal slice from, the radius of the cone is always going to be equal to the height above the base where we cut our slice from. So that's kind of cool. All right, and looking over here, so this is the radius of the sphere at the cross section S, and we know the distance from anywhere from the center of the hemisphere to the outer edge of the hemisphere is the radius, right? So that's R. And then the height is H. This is a right triangle as well. And so we can use the Pythagorean theorem, which is right here, that S squared plus H squared is R squared. So we just studied the Pythagorean theorem in chapter 8. So hopefully that's fresh in your mind. So now the question is, how does this help us in our proof? We're trying to show that pi s squared is equal to pi r squared minus pi c squared, right? Where s is so this is the area of the hemisphere at the cross section, equals the area of the cylinder at the cross section minus the area of the cone at the cross section. And so you're looking here, oh, okay, maybe we can do a little algebra. So because H and C are the same, and we have this, so let's do a little manipulation of this here. First, what we're going to do is we're going to divide both sides by pi, right? We can do that. So when you divide both sides by pi, you get pi over pi here, and then you're dividing every part over here by pi, or you could rewrite it using the distributive property. So pi times r squared minus c squared over pi. Either way, it's going to simplify to s squared equals r squared minus c squared. Hopefully you understood the algebra there. Now, because H and C are the same, right? We showed that H and C are the same because this is an isosceles triangle. So H and C are the same. We're going to substitute H for C. So we're going to get S squared equals R squared minus H squared. And when we do that, we're looking at this right here, and we say, are these two the same? Well, if we add H squared to both sides, I ran myself out of room, we end up with S squared plus H squared equals R squared. So our conjecture, the area of this hemisphere equals the area of the cylinder minus the area of the cone at the cross section. We just showed that algebraically is exactly the same as what we have represented here with the Pythagorean theorem, S squared plus H squared is R squared. So therefore, because of all this, we know that pi s squared equals pi r squared minus pi, pi c squared. Because we could, just like we went from here to here, we could go the opposite way. We could multiply every part by pi. We could substitute C in for H. Does that make more sense if we had done it that way? Meaning, if we go from here, right, this statement here, we go from here and work backwards to get to this. So we would multiply both sides by pi, every part. We want it to look like this. Now we're going to subtract pi h squared from both sides. So pi s squared equals pi r squared minus pi h squared. And then because c is h, we showed that, we can substitute, and we end up with pi s squared equals pi r squared minus pi c squared. Is that easier to understand? I don't know. Anyway, I did it both ways, so hopefully that helps. So our conclusion, this is going to be based on Cavalieri's principle. So we just looked at Cavalieri's. So we'll flip the page back here. So looking at Cavalieri's principle, we showed that if you have different three-dimensional objects where the base and every cross-sectional area have the same area, and the prisms have the same height, then they have the same volume. Okay, so we're going to apply that idea here. If two solids have cross sections of equal area for all horizontal slices, then they have the same volume. That's based on Cavalier's principle. So no matter where we cut this horizontal slice from, we have showed that the area of the sphere in that slice is equal to the area of the cylinder minus the area of the cone. So no matter where we cut this slice from, this circle area subtract the cone circle area equals this circular area, the green, the sphere, hemisphere. So therefore, the volume of the hemisphere is equal to the volume of the cylinder minus the volume of the cone. So this is areas. We're using Cavalieri's principle to say if this is true about the area of these cross sections throughout the whole figure, this whole shape. Okay. If we started as it were at the base, and we said, okay, at the base, the area of the cylinder is pi r squared. The area of the hemisphere, because the hemisphere base is the same, is pi r squared. Subtract the area of the cone. So if we take the cross section of the base, the cone is just a dot. It has no area, right? It's the very tip of the cone. So that would be pi 0 squared. So does pi r squared equal pi r squared? Yes, indeed it does. And so then we could go through every cross-sectional piece and we would show that this is true. Okay? And so what they're saying is if this is true for the entire picture, our entire cylinder, then we can just sum up. If we summed up all the areas of every cross-sectional piece of my cylinder, then that would be the volume of the cylinder. That's what volume is. It's basically taking all your areas and multiplying it by the height. So the volume of the whole cylinder is pi r squared h, the height, but we know that r is our height. So we said the volume of our cylinder is pi r cubed. Now if we take the volume, all the areas of our cone, we said we knew that our cone was 1/3 pi r cubed. And then the hemisphere, that's what we're trying to figure out. So let's think about that a second. Going back here, we can use this formula actually to help us out. the volume of the hemisphere equals the, hemisphere equals the volume of the cylinder minus the volume of the cone. So if we take the volume of the cylinder, we said was pi r cubed right? Pi r cubed, and we subtract the volume of the cone, 1/3 pi r cubed. Well, remember that this is really, we don't write it here, but really have one, sorry, hard to see, 1 pi r cubed. And so to subtract fractions using the same denominator, so really what we're saying is 3/3, that's 1, right? We have 1 pi r cubed minus 1/3 pi r cubed. So 3/3 pi r cubed minus 1/3 pi r cubed equals 2/3 pi r cubed. So this is the volume of the hemisphere. Okay, now our question really is, we want the volume of a sphere. So because two hemispheres make a sphere, the volume of a sphere is going to be 2/3 pi r cubed times 2. So that's 4/3 pi r cubed. So that's our answer. That's our volume formula for a sphere, 4/3 pi r cubed. And you get that from looking at this idea of a hemisphere and a cone and a cylinder, because we knew the volume of a cylinder, we knew the volume of a cone, and we used that to find the volume of a hemisphere. And yeah, since 4/3 is our favorite fraction, because 4/3 of all people don't understand fractions, just a great way to remember that formula. Okay, you might need to go through this slowly to kind of process what's going on here. If you have questions, please email me. Your homework, in addition, this is from 10-8. I'm also going to give you some homework from 10-7. So 10-7, 5 through 16, 10-8, 1 through 13, 17 through 20, 22 through 23. So again, email me with questions, and hopefully that helped.